Thank you all so much for joining and being here today for our first seminar of the term. Today we have Dieter Fox, who is a professor here at the University of Washington, but previously has also been the director of robotics research over at NVIDIA and has recently started a new position over at the Allen Institute for Artificial Intelligence, also directing research there. So we are so pleased to have him here today to talk to us about robotics and integrating that with artificial intelligence. And without further ado, I'll go ahead and let Dieter take it away.
Yeah, thanks a lot for inviting me, and thanks everybody for coming. Yeah, I've been in computer science since 2000, and as you just heard, then I spent from 2017 till mid this year 8 years at NVIDIA, where I led a kind of a half-time, part-time position, robotics research work there, and now joined AI2, Allen Institute for AI. And today I'm going to talk about a lot of work that we've done over the last years, also kind of while I was partly at NVIDIA and part at UW. It's very much about robotics in the age of AI, I would say. And it's what's fitting about the title here, Data-Driven Seminar, is that if you think about robotics these days and what many of these companies are aiming for is really all based on data, right? It's just kind of acquiring as much data as you can so that we can train these complex robot models so that they can hopefully at some point perform useful tasks for us.
Sorry, Dieter, on Zoom,
Something's
there's a blank
missing?
screen.
Oh, okay. I am sharing the screen.
Maybe just stop sharing and share again.
Okay. I can also, let me see if
Sure.
let me share just PowerPoint.
Okay, that's showing up for me now. Sorry to
Okay.
interrupt.
No, perfect. Okay. Throughout the talk, if you have any questions, please feel free to ask. No problem. Okay, let's get started. So, and in robotics, my specific area of focus is on robot manipulation. I did some early work that was mainly focusing on more navigation kind of topics, but on the long run, I think if you want to have robots do useful things in, for example, our homes, things like that, it's clearly important that they are able to manipulate things in the real world, right? Because just moving from A to B is not sufficient to do useful tasks also in many industrial settings and things like that. I guess we can all agree that the progress we've seen in, let's call it generative AI, be it about large language models, vision language models, ChatGPT, but also in models that generate videos and images has been, I mean, truly astonishing, right? When ChatGPT came out, I think virtually everybody was really surprised by the capabilities of these models. We all agree they're not perfect, but the progress that we are seeing is just really amazing, I think. And I think the key ingredients that made that possible is, on the one hand side, vast amounts of training data, right? And the training data is not just, let's say, whatever, random things, but for example, for the language models, it's, let's say, a text on the internet. And the idea is that, of course, the text was typically written by humans with some purpose in mind. So it's not just, oh, I'm getting feedback here. Let me, oh, I should unmute myself. Okay, so it's not just random collections of words, but it's text with meaning. And these models can then use the text by just learning kind of to predict the next word based on the history of words you've heard, right? They can learn to predict the next words. And if you train that on sufficient data, then what came out of that with ChatGPT is really some kind of notion of you can throw any task, any question at it, and it comes up with a kind of reasonable answer, right? Again, not necessarily the true answer or perfect, but it was very surprising how capable it is. And the idea is that the training data is so big that whatever task we can throw at these models is almost in distribution for the model, right? So it doesn't have to truly extrapolate to totally new tasks. At the same time, of course, on the models themselves, these very large transformer-based models are very capable large-scale models that can also digest all this data. That was, of course, also a key ingredient, together, of course, with the compute, like GPUs, right, that really made the training and inference of these models even possible. And then the technique that they're using for training is, from a robotics perspective, we call it kind of behavior cloning, which means the model is trained to replicate kind of what it sees in the training data. Okay, like generating text. Now, from a robotics perspective, we must say that robotics is clearly lagging behind that, right? So we haven't seen anything like ChatGPT in the context of robotics yet. And the question is, what happened, or why is it so hard, right? There's, on the one hand side, is something robotics called, it's Moravec's paradox. Hans Moravec was a faculty at CMU. He came up with this notion that the hard problems are easy and the easy problems are hard. What that means is, coming from an AI perspective, the things that we thought would be really difficult are, of course, the things that are hard for humans, like playing chess or playing Go, right? This is, we say, like, this is the crown jewel of human reasoning or something like that, right? And we thought that that must also be hard for computers. It turns out not so hard for computers, right? But the things that are really trivial for us humans that we don't even think about, those turn out to be the difficult ones. And those are physical interaction with the world. So, for example, picking up this cup and then pouring liquids and water and stuff like that is extremely difficult, right? But of course, for us, we do it just totally intuitively, right? You can also make this connect system 1 and system 2 reasoning, if you heard about that. But again, the things that seem easy to us are actually very, very difficult to get working on a robot. My hope and hypothesis is, and that's also the hope, of course, of many people in the community, is if we could just generate huge amounts of training data, demonstration training data, that is suitable, that is kind of corresponds to the language training data that the internet provides. If we could provide such large amounts of data and train these kind of models that were so successful in language and vision, then hopefully we could get robots to be far more capable than they are right now, right? That's kind of the key idea of many of these companies out there also, right? Like, you might have heard humanoid robots like Tesla, Figure, 1X, many of these companies, they also are based mainly on that hope where we say, if we can just generate enough training data, then everything should be fine, okay? And I actually partially also myself buy into this, where I think if we could just get enough data, I'm sure the robots would be far more capable than the ones we have right now. But there are caveats to this. And also, I don't think we're going to necessarily solve artificial general intelligence by that approach. There's many kind of components to reasoning that kind of approach doesn't really capture. Now, the main questions that come up in this context, of course, where are we going to get the training data from, right? And the training data in this context need to be some kind of demonstration so that the robot can just replicate this data. And what kind of models can we train on that so that they are suitable for robotics? And these are kind of two aspects I wanna talk a bit more about. You might have seen social media, somewhere in news articles, all these success stories of robots doing pretty cool tasks in these videos. Also, again, for example, like Tesla, where the robots pick up things or do little tasks in industrial settings. And those were kind of based more or less all on exactly the same idea, where you have a robot and you want it to do a certain task. And what you're going to do is you set up a teleoperation system, which lets you remotely somehow control that robot. It's a little bit like puppeteering, okay? And then you have a human perform that task many times. So the human controls the robot so that the robot can pick up something, okay? And then they collect many hours of demonstrations, and then they train these models to kind of replicate those demonstrations, meaning the input to the model is an image that the robot has seen during the demonstration. It's also maybe a description of the task, what the robot should do. And the output is control signals that the demonstrator kind of sent to the motors of the robot. Okay? So it's just the same as a language model, where the only thing is what you have to replace is the language tokens by images, and the output is kind of maybe control actions for the robot. And this is mainly what these models are then based on, these ideas, okay? And again, we're seeing actually surprisingly strong results on these. One thing that you don't see when you watch these videos is how brittle these systems still are. So they often work in a very narrow setting if the objects are placed at the right locations and it's the right kind of objects and stuff like that, but they don't generalize beyond that. And that is simply because they didn't have enough time to teleoperate their robots. Okay, so for example, Pi, might have heard Pi 0.5 model, they trained their models, and it's not small data sets, right? So they trained their models, I think, on significantly more than 10,000 hours of teleoperation. Okay, so but even that kind of data doesn't fully scale. So if we look at the kind of sources of data that we could use to train robots to perform these tasks, then on the one side, you could say, well, we just let them watch videos, right? There are all these videos out there that tell you how to cook or how to do something, how to repair your car. So the idea would be, if we humans can learn from that, why can't our robots learn from that, right? On the one hand side, I think it's a really powerful idea because also there's just so much data out there. But at the same time, even if you use computer vision techniques to do like things like hand tracking and recognizing the person and what the person is doing, the gap between what you see in this video and what a robot should then actually do to replicate that is just still very, very large. So we're seeing some early successes there, but this approach still has a long way to go. Again, it's this notion of it's trivial for us humans, right? If we see someone cooking, well, at least we can replicate the basic motions and what we saw in the video. Transferring that to a robot is much more difficult. But on the long run, I think that's a very promising direction just because it provides that huge amount of data. Alternative is what I just described on the previous slide, real-world teleoperation, right? You just put your robots in all these scenarios and let them do tasks. For example, 1X, one of these humanoid companies, they put their robots actually in people's homes, apartments, and let them do whatever tasks the people come up with, but they do it through teleoperation, right? So they have a remote teleoperator and it controls these robots. And then they hope that if they do this long enough, then they have enough data to have the robots do it autonomously because they can train the models on that. The key problem with that approach is, of course, teleoperation and data collection is just very, very expensive, right? Yet another source is simulation data, right? Where the idea is there's now very good kind of physics-based simulators out there where you can simulate, for example, like how a cube behaves in a robot hand and things like that. And the idea is that in simulation, we might be able to generate training data in a much more scalable way because you don't have all these constraints from the real world. Okay, so the idea would be we train robots in simulation and then they just can do the same things in the world, right? The key limitation there is what is called the sim to real gap, which means even if your robot performs really well in simulation, but there's always some differences between the simulation data and the real world data. So which means if the robot now, instead of getting a simulated image as input, it gets a real world image as input, there's enough discrepancy between those that the policies you train on that don't transfer. Okay, make sense? So again, but these simulators, they don't just, the focus is not just on, let's say, the physics simulation, but also on the rendering and things like that, right? Because you need to generate training data that simulates what the robot's camera would see, for example. Okay, and I'll give you some more examples of that. So ultimately, I think all of these sources are going to be very important, and we're going to have to combine them. I'm going to give you a bit more information on the simulation side of this, just because that's what I've been focusing on over the last years. And it's also because I hope that that is a very promising way towards scaling these systems to generate the data that we need. Okay. Oh, and then in the second part, I'll talk about kind of what like such a model might look like once you have the training data to do the kind of high-level reasoning and the low-level robot control. But let's first talk about a simulation. So imagine you want to train your robot to do something in the real world, but you want to train it in simulation. It turns out we have good tools for that nowadays. So what you see here on the left is, imagine you want to teach your robot how to pick up that red object there. Okay, and might be a bit small, but there's certain shapes. This is from a YCB data set, the potted meat can, I think. But imagine you have, for this object, you have a shape model, okay, that you can put in your simulator. You have the mass of the object, you have the surface friction parameters and all of that. And you wanna see how I can train a robot to pick this up if it sees that object in the real world, okay? What you can do is the following. Let's say you have your object model. Let me take that as my object model, right? And now you have a model of a robot gripper, okay, that can open and close and move around. And the robot gripper also has, of course, certain forces it can exert, and the surfaces have certain friction parameters and things like that. So what you can do now, if you go really brute force, is you say, okay, here's my object, and I'm gonna randomly generate gripper poses relative to this object. Okay, I'm gonna randomly generate one, and then I'm gonna say, now I'm gonna run my physics simulator and say, what happens if I close the gripper? Okay, and in some cases, my random guess was good, because if I close the gripper and move it, then the object stays within the gripper, right? But many of my random guesses are gonna be wrong because they're just not gonna be able to grasp it. Is that clear? So now imagine I do this 1,000,000 times, and I'm gonna get whatever 10,000 gripper positions for this object that seem like they would work. Okay? And that's what we're doing here, where we're just doing these kind of gripper trials based on random gripper positions. And the good thing is, again, with NVIDIA, in simulation, you can do this in parallel on a GPU. Okay, so you can thousands of them in parallel. That's the only way how you can really scale that so fast. Okay, so now what we're getting out of this is we get a data set of objects, object shapes that are all annotated with grasp poses that will work on them, right? Because we can replicate that for, in this case, we did it for almost 9,000 objects. So we had 9,000 object models. For all of them, we tried all these grasps and retained the ones that where the physics simulator said, yeah, that's a good one. Okay? But that's not quite enough yet to train a model on that, right? Because we need to simulate what it will look like to a robot when it observes that object. What we can do then is actually pretty easily, we can take our simulation environment. Let's say you put a tabletop in your simulator and you put the object into that scene, your simulated scene. And again, for this object, you know where the good grasps are. Yeah. And then what you do is the following. You take, you render the scene as a point cloud, which is kind of a depth image, which is a camera image that gives you kind of information about the 3D shape of things. So you say, this is what the scene looks like. And that is the input to your deep network transformer. And the desired output is the 60 position of the gripper that will succeed in picking up the object. And I'm saying 60 because it's not just 3D position, but it's also the 3D orientation. Okay, so input image of the scene, output is all possible ways of 60 gripper poses that will succeed in picking this up. That makes sense? Okay, and also important, the input is what we call a depth camera image, which means that is exactly the kind of representation that we would observe in the real world with a robot if you put one of these so-called depth cameras on it. Okay, and we did this here, and we did a sequence of different papers. But then what you can do with this is the following. You say, here's a scene, the robot, there's like objects in the sink. And we can also, for example, tell the robot which object it should pick up. So here in the upper left corner of that sequence here, you see an image of the object the robot should pick up. Okay. And then you see these other two images next to it. These are the images where we have one that is next to the robot observing the scene, and another is kind of a gripper camera that's on the gripper of the robot. And what you see there is in green is a mask that we can automatically generate for the image, saying like, okay, given that you want me to pick up this little pen, this is where the pen is in the image. Okay, and then we can feed that into this trained network that provides us grasp poses. And once we generate these grasp poses, we can run motion planning to go there and then pick it up. Okay, so now we got that one. And you'll see now we have a different target object. For example, here it's like this white bowl. It's segmented in the image automatically. And because we trained this model to generate this grass, the robot has just to figure out like how to move there and then go there. Okay. So important that I didn't go into the details here, but every single aspect of that system was trained in simulation. So that robot has never seen real world data, but because the way we did the simulation and the training, it actually works reasonably well in the real world. Okay. And the key trick was that we're leveraging simulation to scale the training data up, right? Here's another idea of how you can generate large-scale training data for a certain task. In this case, imagine you wanna, how can I get rid of this? Yeah. You wanna like put a book in a shelf, right? Or imagine at home, there's your pantry and you would put a can in the pantry, okay? And we wanna teach a robot, he needs to pick up the object and then place it where there's enough space to put it, okay? How we can do that is the following. In simulation, down here on the left, we can easily generate millions of bookshelves, not hard, okay? Where this is, for example, is an example of a bookshelf. And the books are represented here just by points on their surface. It's what we call a point cloud. Okay, so it's kind of, we only care about the shape of the books, not so much the content or so. Okay, and in blue, you see one of the books that's kind of just nudged in between these other books. Okay, so what we would like to teach the robot is if it sees a book, how it would fit it into this little gap between other books. Okay, so it turns out it's pretty easy to generate a scene like this. And now what we're doing is we're just going to say we're going to add noise to the position of this book. So you can see in the sequence that the position of this book deviates more and more from where it fit into the shelf. Is that clear so far? Okay, and doing this is trivial because we're in a simulator and we just randomize stuff. Okay, and now what we're doing is we're going to train a deep network again to undo that noise process. You might have heard of diffusion models, flow matching models, or things like that, which are, for example, if you heard of models like Sora or any of these image generation models, these are mainly diffusion style models where they train them by taking a real image and then they add noise to this image and then they're training a model that goes from noise back to the image. Okay, so the same way we train these image generation or video generation models, we can train this kind of model, meaning we have a scene, we add noise to the scene, and now we're training a network to just undo that noise. Okay, so the input to the network is the point cloud of the scene and the point cloud of this object. And let me just show you here on the right what this denoising process then looks like. For example, like this, where I show you these two kind of scenes. And at the beginning, the objects are in a random position. And then the network learned how to kind of wiggle them through this denoising process into place. Okay, which means the start point is kind of a random noise image, and the end point, this would be kind of your clean image generated by one of these image generation models. Okay, let me show you this again. Okay, so the denoising process just figures out how to fit them somewhere. Okay, and once that model is trained, because it's also trained with point cloud data that we can observe, it actually transfers pretty well to the real world. So now that robot picks up an object and can figure out where in that shelf it would place it. Doesn't always work. We're not perfect, but pretty reasonable here. Okay, we can also look at some other kind of scenes here. Of course, also works with books. Again, where the trick is, we know how to pick it up, and then we know where to place it based on this denoising process. So that's another example of using these simulation kind of environments, right, to just generate that training data that we need that's appropriate for these robot tasks. Here's one other task, like hanging the mug onto those, where we also use this denoising process to know where we would put the mug, okay? All right, one more example is from industrial application use cases. So far, spatially, the tasks that we had were pretty forgiving, okay? It turns out many of these industrial assembly tasks, they require very, very high precision, right? So for example, if you want to thread a nut onto a bolt, that you need to have like sub-millimeter precision to get it on there so that it doesn't get entangled and things like that, right? Or if you want to insert something in with very tight margins, that turns out to be actually very, very difficult, even for robots. Okay. And for instance, like NIST came up with this benchmark for robot assembly tasks where they have like things like here in the front, you see this threading a nut on a bolt, or back here is like gear assembly where you have to put a sequence of gears together, or like whatever, plug in an Ethernet cable, right? It turns out it's not trivial for a robot. So that is why most of these tasks right now are still being done by humans, all right? And the idea would be, can we train robots to do these, but in a somewhat flexible way? And when we started this, we thought, yeah, of course, we're going to use simulation again for this. And I was naive enough. I thought, can't be hard to simulate these kind of things because it's so well specified, right? You have a nut and you have a bolt. How difficult can it be to simulate that? It turns out it's much harder than maybe you might think, definitely than I thought at the time. And it's very time consuming, actually. So at the time, the best technique for this was this one here, which, let me show that again. So this looks kind of simple, but in order to simulate that, you want to simulate that from first principles on, which means you apply certain torques to the bolt, right? And based on frictions and the shape of the thread, it kind of makes that motion, right? And simulating that with all the contact modeling and everything, they were able to do this with a kind of toy setting. It didn't have quite the precision for industrial style stuff. But the problem with their simulation was that it was 350 times slower than real time, which means to simulate 1 second of threading a nut on a bolt, it took them 350 seconds. And that, of course, somehow beats the purpose of using simulation in the first place, because typically we want to use simulation because we can do things very fast. Okay? So I was at NVIDIA. We talked to the physics simulation guys, how we can take advantage of GPUs. And with some tricks and stuff like that, they were able actually to get it to a speed where we were then able to simulate 1,000 of them in parallel and in real time. So we didn't get just the 350 times speed up, but we also got 1,000 times speed up because we can do 1,000 of them in parallel. Okay? So, and these were really kind of with the precision that you would see in a real nut and bolt setting in the real world. Okay? And the nice thing is, once you can simulate that stuff really fast, we can start doing reinforcement learning. Okay, we can use the simulator to train a robot to try to do this. Okay, I don't know how much you know about reinforcement learning, but it's this idea where you set up a task by designing kind of a reward function. What does it mean for the robot to succeed by doing something? And it takes still a lot of effort to set these things up correctly, but then the robot can kind of by itself more or less learn how to solve the task. Okay? And here are some examples then. We were able to train these policies in simulation, but also we were able to transfer them to the real world. So here in the upper cases on the left, these are simulated assets, what we call simulated settings for insertion tasks. And on the right side, you see the corresponding situations in the real world. and how the robot can then insert these tasks. Okay. So the interesting aspect here was that we were able to do the training fast because we had fast simulation, but also in a way so that it transfers to the real world. Here's another a bit multi-step kind of sequence of tasks that hints at least a bit more at this assembly. And in this case, this was not, let's call it blind execution by the robot, but it did use also visual feedback to figure out where the assembly piece is. And in this case, also where, like, once it inserted the first piece, now it takes these little gear pieces and places them in there. And that whole process was trained in simulation. Okay, the whole controller. And you can see if we go a bit further on at some point now, it also starts threading in these nuts. Okay. But you can also see that that is clearly not the speed that you need for a real industrial setting, right? So it's still pretty slow, but it's ongoing research. Another thing that comes up is what kind of sensing should the robot use? In this case, wait, let me stop that briefly. The robot has, you can see this, can you see my mouse here? The robot has, it's a touch sensor, tactile sensor. So it's a special sensor that lets it give kind of, because our human hands are full of sensors, right? To contact sensors. And so there's some efforts in putting such kind of sensors also into robots. And then the question is, how can we simulate these sensors and how can we do this sim to real transfer? And we were able to do that actually pretty well too. Okay, so the robot was leveraging the tactile, this touch sensor, in order to do this insertion task here. And again, being trained in simulation and then executing in the real world. All right. Now, just briefly, kind of to summarize that section, first of all, I think it's very promising to see that we can start really training robots in simulation. There is still various limitations with, for example, what kind of phenomena can we simulate very well, right? I think liquids we can simulate pretty well. Deformable object simulation is also getting better and better, but that is typically very slow. So it's not fast enough to do the kind of training that we need. And simulating like all these everyday phenomena and all these things that we see in the real world is also, we're not quite there yet, right? So what works very well is kind of rigid objects, how to simulate and how to manipulate them. So, but now once we have simulators, how do you use them to generate that training data? On the one hand side, again, we've seen some very promising work on reinforcement learning. It turns out that most of the humanoid robots or the legged robots, their locomotion capabilities are all trained in simulation, actually. So they all use more or less this reinforcement learning techniques to train the robots how to go robustly through different terrains and adapt on the fly. And those policies actually transfer really well to the world. These work way better than anybody trying to explicitly model like what it means to make all these contacts and how to react to it. Because if you go outside, the kind of terrain and the surfaces you have to interact with is just way too difficult to explicitly model, right? So what they do then typically is they train these in simulation. And one key trick is to get this sim to real transfer is what we call randomization, where in simulation you can just randomize parameters of the world, right? You can say how soft something is, or you can slightly randomize or perturb the mass of the robot and all these things. And if you learn policies that are robust with respect to that randomization, then they actually transfer pretty well to the real world. Yeah, because from a distribution aspect, the real world is kind of within the distribution of your randomized simulated world. Yeah. Another technique that people are deploying is teleoperation, right? Where you have a simulated robot and now you teleoperate it, the way we also teleoperate real robots. One limitation, I think, there is, of course, that the scaling is still the issue, right? Because you still need to teleoperate them all the time. So I think this is good for maybe generating specific training data, but for scaling purposes, I don't think that's necessarily the most promising approach. Another approach is something that we've been investigating a lot is using planning techniques. For example, it turns out that there is, for example, if I want to plan for a robot for my hand to get to a certain location and pick up an object, that motion, you might argue, I don't need actually a learning technique because we have optimization and sampling-based planning techniques for solving these tasks. However, they only work if you have perfect information about the environment. The good thing is in simulation, we have perfect information because a simulator knows everything. It knows everything about the shape, it knows where the objects are, it knows their masses and everything. So the idea is, can we deploy techniques that don't really work in the real world, but can we deploy them in a simulator to generate training data that we can then use to train these networks on, for example? And that's a technique that we've been using quite a bit, also very successfully, actually. I think that's very promising moving forward. Okay. And another trend right now is, of course, using generative AI in this context, where one problem with simulators is often where do you get the assets from? Like, for example, where do you get a shape model exactly of this iPhone or something like that? And how do you get that in a scalable way? There's now using similar techniques to the ones that are generating, for example, images and videos. You want to train them to generate 3D assets that you can put in your simulator and things like that, right? We're also starting to deploy large language models to generate tasks in a simulator. So for example, we do something at AI2 right now, even for like block stacking, right? You can then actually tell an LLM, okay, we have a simulator and we want to simulate, let's say, certain blocks. Give us a task related to stacking. 1 second. To stacking. And then the LLM actually can be prompted to come up with a description of the blocks that you want. It tells you where they should go in the simulator. And it also tells you, for example, okay, we want to build a stack of 3. And it tells you even the conditions that would be verified if you succeed at the task. So these LLMs are very, very powerful even in this context now. Yeah, you had a question. Can you speak up a little bit?
Yeah. So for the asset generation, does it also generate like the physics of the asset, or is it just a visual model?
Yeah, no, it's typically now, let's say, what they're reasonably good at by now are the 3D shape of the objects. That's a key focus. And then you can also, for example, for the mass of the objects, you can also query an LLM like, okay, how heavy is typically a coffee mug or something like that. There are these kind of different approaches. But the caveat is, I would say, we're not quite there yet, right? There's often things are just wrong and they don't work well in a physics simulator or things like that. So this is just kind of a starting trend, but it also, I think, is pretty promising. Before I move on, any questions about this simulation side? Yeah.
During the past slides, it was like you generate noise for the robot to like put a book by the bookshelf. And how exactly does how do you turn the noise into robot's motion into putting the book in the bookshelf?
Oh, in this case, yeah. So this was actually, we did not. Okay, yeah. So the question was, for example, in the book shelving task where we generated noise to perturb the position of the book. The question was, how do we translate that into robot motion, for example, right? In that case, actually, the process was solely to figure out where the book should go. And the motion of the robot itself was generated by a planner afterwards then. But there's also a lot of work going on. Many of the successful models right now, they actually use exactly the same denoising model, like flow matching kind of techniques that actually generate explicitly directly joint commands for the robot using the same kind of techniques.
And a follow-up question, like when you were denoising the position of the book, there was no like physics involved. Like the book was floating on like the bookshelf, and that's fine.
Yeah. For all of this, yeah, in the end, it depends on how dynamic the task is and how much it depends on how robust it is, right? So if it would turn out that the books, if they're a little bit above and you just say, that's my denoising process is done, then it might fail and you would have to think like how to get it more accurately there. But again, one of the key applications right now that we're seeing that's really successful is using this teleoperation data and using this denoising style models in order to generate output commands for the joint motors of the robot directly. Okay, so now I want to give you an idea of how we can combine these kind of models that I showed so far, which are mostly kind of very specific tasks, right? They're like you want to pick up an object or you want to place a book in a shelf, but there's no LLM style reasoning going on so far, right? It's kind of like very specific tasks, and it's not this kind of open world reasoning that we want to see. So let me give you one example of a model that we developed that is now going in this kind of direction. Okay, so the first question is, if we have these large language models or vision language models, how can we leverage them for robot control or robot planning? Okay, the first line of work, and we also did some examples there, is this here on the left, where let's say you see this layer, let's say we have robot skills, which means I, as a roboticist, I program certain skills for my robot, which is, for example, pick up an object. So the skill would be pick up parameterized by something, right? Or place an object or slide an object to a certain position. Okay, let's assume I have a discrete set of these skills or function calls if you want. Okay, and then in the early work, what we did was you take an existing large model like ChatGPT or so, and you feed it the text, the command, what the robot should do, and the image of what the robot currently sees. And then you just ask your VLM to output almost like we did even a Python code that says, okay, for this task, like to get whatever, to get this cup in the trash can, for example, the output would be something like, okay, pick up cup, right? Maybe with the coordinates of where the cup is, and then move it over and release it or something like that. So it's really kind of Python code, high-level Python code that calls these functions that we already implemented as robot skills. So I would call this kind of like a loose integration between these two paradigms because it requires that these skills are already predefined and everything. Another approach is, we've seen this several examples of that. Also at AI2, we just released one called MolMoAct, which is just a real one big model end-to-end that does everything. So you feed it in text, images, and maybe information about the joints of the robot, and the output is direct control commands for the robot, like all the way in one pass, kind of, right? There might be some reasoning going on, but more or less just one pass. Ultimately, this is whatever your large models for language might be doing already or something like that, right? The problem with that is often it's really hard to control these models and to understand when they don't work, why they don't work, right? It's really hard to get enough training data that's appropriate for this. And also, you can imagine the high-level reasoning sometimes, if this is a very large model, it might take it 1 second to go from image to control. And a frame rate, a control rate of 1 second might clearly not be enough to actually control a manipulator, right? So the problem is by mixing the high-level reasoning and the low-level control into one big thing, you're also kind of limited by the frame rate of what your system can do, right? So the paradigm that we've been following with this most recent work was more where we say we have two models, where on the top we have a vision language so-called action model, which is one of these very big models, trained internet scale, but the output of the model is not direct motor controls, but some kind of information that tells the low-level model what to do. Okay, I'll give you a bit more information on that. And then we also train low-level policies that actually execute then these 3D commands so that the robot can whatever, pick something up. But again, these policies get guidance from the high-level model on what they should do. And the advantage would be that, for example, the high-level model might be updated whatever every second, but you could maybe run the low-level model at a much higher frequency or things like that. Okay? And this is kind of what we did with the so-called hamster model, hierarchical action models. So here's kind of the idea. Text images goes into the large model. and then into an interface for the low-level policies. In Hamster, what we did was the following. The large model was trained to take in images and a task, for example, put the wine bottle in the wine rack, and the output would be a sequence of points that kind of represent the trajectory the gripper should take in order to execute that task. Okay? And this trajectory or trajectory sketch importantly was in 2D, because these high-level models, they're very good at 2D reasoning, 2D image reasoning, but they're not so good at 3D reasoning yet. Okay? So then this 2D trajectory sketch is fed into a low-level policy that then tries to come up with the actually action commands that execute it. Okay, so the key idea is, again, the high level is trained at internet kind of level data. It performs high level semantic reasoning, and the low level performs more like the spatial fine-grained reasoning. And how these fit together then is the following. Imagine you have the task, put M on Mona Lisa, a very natural task here, obviously, right? And you can see there's a block with the M on it, but we don't send it. So the only input to the model is put M on Mona Lisa and this image, what the robot sees. So we feed this into our large model, the VLM, Vision Language Model, and the VLM generates actually in text, as text, these coordinates, if you look on the left image, that now represent what the robot should do. Okay, so the high-level model says, okay, to put M on Mona Lisa, this is where the gripper should move, kind of. You see that? And blue indicates the beginning, and red indicates the end of the trajectory. And the circles also indicate points where the gripper stage changes. So for example, in this case, what it means is at the blue circle, move there and close the gripper, and then move to the red one and then open it. Okay, and then we take that image and the trajectory and add into it 3D information that we can get from the sensors. And we're also refining the language command to be more generic. Rather than saying put M on Mona Lisa, we tell the low-level model, pick up an object and place it somewhere where the context which object to pick up is given through the trajectory, right? So for example, we don't want the low-level model to have to reason about Mona Lisa and things like that, right? We just want the low-level model to reason about, okay, which object should I pick up? Okay? And then that goes into a policy that we train, and the low-level model can actually do this. Yeah.
Is the new text prompt also decided by the high level VLM?
Which prompt?
The pick up the object and click somewhere, is that translated from?
That's automatically translated, yeah, as well. Yeah.
LLMs are notoriously bad at numbers, so does it come up with the coordinates?
You know, the VLMs are getting better and better at that. Also, like if you look at the Google DeepMind, the Gemini models, and so we started some of this with the first work RoboPoint, where we trained models to point at certain things in the image, to identify certain things, objects in the scene and stuff like that. And if you give them enough training data, they're actually getting pretty good at these things now. But so they're good at these 2D image coordinates, but they're still not quite good at the 6D pose coordinates for robots. That's why we have this two-layer approach. Okay. So now the question is, how do we train the high-level model actually? How do we teach it to generate these trajectories, right? Because we need training data for that. So we do this the following. There are various data sets out there that people collected with real robots. Okay. The ones we use is one's called Bridge and Droid data sets. But you can see here, it's like they have 320,000 trajectories of robots executing something. So that data set, for example, if you look here on the left, you show that scene, and the task is move the green object in the silver bowl. And then it contains a video where someone teleoperated the robot, important teleoperated robot to do this. Okay, we can now take that video to extract a 2D trajectory from it, right? Because we can track the hand, and then we just overlay a 2D trajectory on that image. Make sense? So now we have a training example for our vision language model, where we say, if that's your input and that's a command, this is the 2D trajectory you should generate. Okay. We can also do this for simulated data. Okay. Do you see these trajectories here? So we can automatically generate those. And now we train a VLM on that. And it's doing actually pretty well. I'll give you just a few examples here. So that's, I think, one of my favorite scenes. So for example, imagine you show that scene and the task is move the S to the plate the arrow is pointing at. If you would have to kind of manually parse this and identify the objects and stuff, it's not trivial, right? Because of course, S and plate is pretty easy, but the arrow is pointing at. So you have to decide that this white image, the white piece of paper has an arrow on it and it's pointing at the red plate, right? So the model successfully comes up with a trajectory that starts at S and goes to the red plate, right? And we're getting that kind of for free because we're using a model that was trained on internet scale data, right? If as a roboticist, you would have to program that yourself, there's just no way you could do this. Way too complex, okay? And here, of course, the obvious counterexample is move the S to the plate the arrow is not pointing at, then the model is actually pointing to the green plate. Okay, so it's doing some pretty nice reasoning there. Here's another example of what we're getting with these models is, here's the task is screw the light bulb in the lamp. And that task was only contained in simulation data. And you can see that that simulation data looks very simulated, right? It's not anywhere realistic, but because this model was trained on so much real data as well, it was actually able to transfer that. And later when you show it that image, it would generate that trajectory for that task. Okay, so which means you can teach a task in simulation and the high-level model transfers actually pretty well to real-world data. Okay, another example here is we had these tasks like push the button with the color orange, and then later it could even succeed on a task like press the big red button, then press the button with color of leaf. So there's two interesting aspects here. First of all, it's different buttons and different sizes, so they look very different from the buttons in the upper image. But also, you could then say the button with the color of leaf, which in the training data, we never identified a button by leaf. We always said green or something like that, right? But again, it's a large-scale model. It can do this automatically. So that's, I think, pretty exciting there. Yeah. It's just one point after the other. It's literally text output, whether the trajectory that the image is generating is in some higher dimensional vector space. And I said it's just literally, it's outputting discrete image coordinates, a sequence of discrete image coordinates, actually as text output, literally. And we can discuss this also, of course, the idea of using this 2D trajectory as kind of this interface between high and low level is just kind of a crutch at this point to show that it's possible, right? Because ultimately, I think that interface between high level and low level reasoning needs to be much richer because 2D trajectories don't convey all the information that you need in there, right? So you could imagine that this could actually be a vector space that communicates between the high and low level, kind of a bottleneck or tokens where the high level generates tokens and the low level uses those tokens as context for what it should do. But for that, it turns out you need significantly more training data to learn this tokenization and stuff like that. So we haven't done that yet, but that's a direction we are looking into. Oh yeah, we evaluated that just briefly. So we collected in the real world some teleoperation data for our robot. There were 3 tasks. On the upper left, the task was like, okay, pick up something and put it in one of the bowls. Okay, like in this case, pick up the energy bar, the Snickers, I guess, and put it in the red bowl. So this was teleoperation training data with which we trained the low-level policy. Okay, and the input to the low-level policy was the task, the image, and the 2D trajectory, right? So that it could learn to interpret the 2D trajectory. The right task is just like, okay, press the right red button, very easy stuff. And down there is push down the drink. Okay, so these were 3 types of tasks, but we can randomize things. We can use different objects and we can use different colors and things like that. Okay, then what we did is, yeah.
How much physical information does the robot get when picking up the candy bar, for example? Does it know not to crush the candy bar because it's getting
No.
No, it's not.
It's way too complicated. No. Yeah. Okay, the question is how much physical information does the robot get or use even to do these tasks, right? And in this case, I said we do actually the simplest where we just have a certain force that it applies and that's it. There's no reasoning about certain objects you should not squeeze or things like that. For that also, you need a better sensor information on the robots. And there's work going on where you use, again, as I said at the beginning, like tactile sensors and also force torque feedback from the joints and the sensors in order to do this. But for this kind of work, it's kind of really just simple pick and place kind of stuff. Okay, so again, we generated manually tail-operated 320 examples of these tasks and changed them slightly, and then tested how well the robot was able to do them afterwards, right? If we change things slightly. So here just sequence of different, where on the x-axis, you see different kinds of things we change between training and testing. Let me just point out 3 of them. Visual, meaning that, for example, in the test scenario where the robot had to execute it later, we changed, for example, the color of the tabletop, or we put different objects as distractors in the scene. Okay, so that the training and test didn't really match well. In the language, we changed the words we used to refer to the objects, for example, right? And in the spatial one, for example, press down the left button means that in the training data, we never refer to an object by left or right, but only by the color. And later on, we wanted to see, can it actually do it if we say the left one? Okay. And the success rates that you see here, this is for 2 low-level policies that were trained on the data and tested under these circumstances. And you can see that they were not doing that well. The green bar is for an existing monolithic open world model. It's called OpenVLA, which is one of those models that I said that takes in images and outputs direct action commands. And these 2 bars, the new ones, this is our hierarchical approach using one of these 2 low-level policies, but now they were trained in the context of the high-level reasoning. So this is kind of shows the benefit we're getting by combining high-level reasoning with this low-level control as well. Okay, so you're getting now kind of the best of both worlds. Okay, let me here's just some of the examples we can do then with this. One that's pretty nice here we did here is, for example, the busing task, where you can do it almost in an interactive mode where you say, okay, what's on the table? Which trash bin do they belong to? And then it sees there are these 3 objects, and which goes in the recycle bin, which one goes in the trash. And then you say, pick up the crushed can and put it in the recycle bin. So we're getting this language interface for free because we are leveraging this large language model for this, right? The language model can understand what we're saying and then send the appropriate 2D trajectories to the low-level control. And the low-level control hopefully knows how to pick up something and stuff like that. All right, so I think I'm right on time here. To summarize, yeah, this question of where's robot GPT? I think, again, we've seen this tremendous progress in the vision community, language community. We're not quite there with robotics, as I'm afraid you've seen here, right? There's still many open questions. I believe that simulation can play a big role in improving the capabilities of these robots, just because it makes scaling of the training data so much easier, and training like things through reinforcement learning. We can leverage planning-based techniques to automatically generate data. Another nice aspect of simulation is that it also enables you to do benchmarking between different models. Doing all this benchmarking in the real world is a real pain, and it's really hard to scale. And finally, the last part I talked about, I think this hierarchical models is a good way for kind of combining this high-level open world reasoning with the more low-level kind of robotic manipulation kind of control settings. So that's a promising direction to go into. And offline, if you want to ask me a bit more which direction we're going at with AI2, but at AI2, we're also going leveraging more simulation, but going really, really large scale. Like the question is, what happens if you could generate millions and millions of training examples and simulation? Would you suddenly see something really interesting happening on your models that you train on them, kind of like towards ChatGPT? And with that, of course, thanks to all the great collaborators, both at UW, NVIDIA, from my lab, and also many interns that we had over the years. Thank you very much.
We're just at the hour, so certainly feel free to go if you need to, but we'll take a couple of minutes for questions, both online and in the room. We'll start within the room. Are there any questions? Yes, you're in the front.
I will ask the data used to training Momo activities from the real world or from the simulation.
Which you say?
Yeah, I see the data using to train the Momo act.
Oh, MOMAC, yeah. So the question was which data we use for MOMAC. It was a combination of actually different real-world data sets out there, and also some specifically collected ones, but also simulation data, everything.
What is combined?
Yes.
Yes, in the back.
The model has to be more complex, right? So I was wondering, like, how does it scale? Is like international training data that and larger the network?
Yeah. The question was about relation between training data and model size, n times more data, n times larger model. And I must say, at this point, I have no real idea, like how it really matches. At this point, we are mainly really starving for data, right? And high quality data. And I think there's hope that the models that we've seen that are successful for language and vision tasks, that so for example, there's no robot models out there that are anywhere at that scale yet, right? So I think the limitation that we have right now is not so much due to the model size or capacity, it's more the data scale that we have. And the relationship itself is just not so clear.
Great.
Oh, sorry, just in the last example, you showed that, because you mentioned, if I understand correctly, you mentioned that the model was able to interpret the coordinates in the picture, so it doesn't have to do the traditional computer vision version of image coordinates to the real world coordinate. It was able to understand that and then program it to the lower dimensional model. Is that correct?
Yeah, so the high level, the question was with what role these image coordinates played, right? So the idea was really that the high level model, which is trained on many, many vision tasks, but often a lot of like 2D vision tasks. So that was only tasked with generating these 2D image coordinates. And then the low level model, it was trained to interpret those 2D image coordinates in a way that kind of guides its generation of the 3D command. So for example, if you have if there's two objects in front of the robot, then independent, so the high level based on the language command figures out which object you want to pick up. And the low level just gets a trajectory that points at the correct object, and it then knows how to pick it up.
Thank you.
Yeah.
It can be kind of difficult when you're building a physics simulation engine to take all of your relevant forces parameters into account. How often have you noticed deltas in the way that like an error was modeled in your simulation engine itself impacting your policies results? Like
Yeah. So how often we see that, for example, errors or approximations in the physics simulator, right? That affects, for example, the policies we train or in general. Yeah. Not quite all the time, but almost all the time. So one of the problems is still like in these physics simulators, there's often just things that are not quite right? And for specific tasks, we've seen that we've gotten actually very good and very close. Again, for example, for picking up objects or the kind of tasks that I showed you that are more industrial, we've gotten pretty far that, for example, we had a paper on where we simulate actually force torque sensing. The simulator generates force torque signals. The policy was trained to take those into account for the task. And that actually we got that to transfer to the real world. But it's not a simple out of the box kind of thing, right? It takes quite some experience on how to set these things up, how to randomize it and everything. So this is still, I think, a developing kind of frontier of what we can do.
So it's mainly mitigated by approximating things close enough and then putting
Yeah.
randomization in your parameters.
Still, yeah.
Does the motion planning decouple from the object, like,
Yeah. There's different approaches. So on the one hand, the question was if motion planning is decoupled, let's say, from the object manipulation and things like that, right? There's different approaches. Some people argue that we just need the high-level model to give goal points to the motion planner and then let the motion planner figure out how to go there without colliding and stuff like that. It turns out that that works to a certain degree for just picking up objects, but many tasks require like continuous interaction with objects and stuff like that. And that is where motion planners typically just don't work that well anymore. And I think the trend is going more towards letting the policies learn even that the motion planning side itself too. That's something we're also trying, for example, right now. Yeah.
Is there any like efforts towards a 3D model that's capable of reasoning in 3D? Because right now there's still like a bigger model that's controlling a lower level model that's like out from 2D to 3D. So do you see a model that's inherently capable of these 3D reasoning?
Yeah. So the question was if there's efforts or if there's hope for like a high level model that can actually do the 3D reasoning and isn't constrained to the 2D kind of reasoning. And there's various efforts going on. So for example, the MoMA-ACT model that we had at AI2, actually one of the tasks that we used for during training was to predict the depth image, like the 3D shape of the scene that the robot sees. So that's really hard from a monocular image. But it turns out as an additional task, it actually helps the policy to be better. So yes, various teams are working on that. Like even like the Google Gemini and all these kind of efforts, like the large models, they're all aiming to get much better at 3D. Now the question is, does that make this layered approach obsolete? I'm not sure because there's still the question of fast reasoning versus slow reasoning and things like that, right? So I think that will still make sense.
I want to be mindful of the time here. We're 10 past the hour, so I don't want to keep you forever. But
That's fun.
yeah, thank you so much for everything, and thank you all for attending and the great questions. If you have more questions, maybe you can reach out to Dieter directly. And thank you to everyone who attended online. I saw that we had over 60 attendees, so that was awesome.
Thank you very much. It was fun.
Thank you. Let's do it again.